set up the whole conservation of energy business and run through that, and then we'll work on this particular problem that we ended with last time. So I can start with, in fact, let's just look at the situation. We're looking at forces that are a function of position only. That allows us to get a potential energy function a to x negative, squeeze that in there, negative sign f x prime dx prime. And when we have that, we immediately have conservation of energy. So this is actually worth playing around with a bit. I'm just going to do it in terms of half mv squared plus u. Let's put a subscript there, equals 1/2 mv2 squared plus u of x2. So the fact that I have the same value at any 2 points in space and time of that system means that I have that constant right there. Okay. So you probably did these in physics 4A, and I thought maybe we should just review a bit. Example, when do you have conservation of energy? Roughly speaking, when there's no friction. Right? For the basic version of this, there's no friction. So say you have a pendulum that's going to just swing through an arc. Pendulum of length L, and it's going to come swinging through here, and it'll be moving, some certain speed. In fact, no, yeah, let's go through that way. Okay. So we're going to pendulum released from rest up here. Okay. Released from rest. Okay, so we release the pendulum from rest. There's our conservation of energy. It's being released from rest. I'm just going to rewrite this. 1/2 m v1 squared plus u of x1. Use of 1 equals 1/2 m v2 squared plus u2. And I'm calling this the 1 position and this the 2 position. I'm releasing it from rest, so I've got a 0 here. Now I have to declare an x-axis, and we know that that's mg x. X is the vertical axis, and it's going to come swinging down here at mv2 squared. And since I made this my 0, I had that freedom. Then I've got a 0 here. And we get the good old result that you would have had from free fall as well. V2 is equal to m's cancel on both sides, root 2gx. And it actually, let's do one more thing here. Since the thing was of length L, I actually had x equals L. I'm going to go ahead and put the L in here. Okay. L, 2gl. Something you just got from free fall, except this time we were swinging around from one place to another. So this is something we learned in the past. You definitely don't want to forget it. You can do roller coasters, things like that. Have you guys done roller coaster type of problems in physics 4A? Something going down the hill, doing a loop, right? And you're just always finding the energy at one place equal to the energy at the other. So that's the basic application. But now we're taking it a step beyond that, and we're going to say we have 1/2 m dx dt squared plus u of x is equal to e. And And this is what we did, what we were working on last time. What we ended up with was dx over dt at plus or minus 2 over m e minus u of x square root. We saw that the plus sign was maybe a positive, or not maybe, could be positive direction minus sign, negative direction of motion. And so that is really just this calculation here, general terms. But the next step was to look at this as a differential equation and separate variables. So that's what we're going to spend a little more time on today. We're going to take this, separate variables, solve for the time as a function of position. And I already set that up as a homework problem, but we'll do a couple interesting things with that. So, separation of variables, solve for dx and dt. Independently, we have the dt. So this here, separation of variables. Same technique we did before. dt, we have dx, and the plus minus still is important. 2 over m e minus u of x. And we can integrate both sides. This just gives us a time, 0 to t. The right side, we're getting the time as a function of that upper boundary there. We'll leave the lower boundary empty for the moment. So that's the time for something to happen in terms of the distance traversed. I can put an A here as well, for what it's worth. Okay, now the example we had was u of x is equal to minus k divided by x. X was greater than 0. That looks like this. Okay. And that was good. That was a Newton potential, so we already did some work on that. See, what I want to do now is consider a more general case. U of x is equal to, I'm just going to choose a letter here, b x to the nth power. So the constant b carries the appropriate dimension. Whatever the energy divided by length to the nth power. Bx to the n. And in fact, I'm going to do a little more here. X to the n magnitude. Okay. We can already see from this example, under some circumstances, x would be positive, e would be negative. Okay, but we're looking at as the general case here where. So this will be a special case that we'll deal with separately. We're looking for these now, and they're supposed to look like, okay, so here's u of x. What do these look like if you have, say, x equals x n greater than 0?
You get a cosine or quadratic or whatever.
Yeah, so you can get a straight line. You can get quadratic. You can get the cubic, except its magnitude. What happens to those curves as n gets larger and larger? Are you guys familiar with that?
It kind of, as I recall, becomes steeper, fatter.
It becomes flatter towards the origin and steeper as you go up. So let's draw a few of these, and I'm gonna make some room here. This one we're gonna be able to get an interesting limiting case. So, n equals 1, there's the start, right? This is n equals 1, that's pretty basic. If we have n equals 2, we have n equals 2, we're gonna be coming up like that. And we're familiar with the parabola. If we have n equals 4, say, it's going to be flatter and then eventually steeper. Flatter and then eventually steeper. Okay. The interesting case, if n goes to infinity or gets very large, it becomes flat all the way across and then it suddenly zooms up. So we actually have quite a few interesting functions here, and I should even bring into play n equals 1/2. N equals 1/2. I should put the n outside here for what it's worth. Okay. Put the n outside. Because then we can have an n equals 1/2, and you guys know it would go up like the square root. Right. Since we're doing the magnitude, we could have it from minus, negative and positive values. So we're looking at our potential wells. Potential wells.
Is the n inside or outside of the magnitude?
Right now it's outside. I changed my mind on that, okay? Because I wanted to have these other powers as well. So that way we get the magnitude always positive and then the nth power. Good. So what about energy in a situation like this? We're going to declare an A and a minus A here, thinking of amplitude. And then those will be our turning points. So if we have 1/2 m dx dt squared plus b x to the n equals e, then when x is equal to plus or minus a, the velocity is 0, those are turning points, and then you're looking at oscillations between, from the left to the right, back and forth. But what this allows us to do is get a value for the e. So e is equal to b times a to the n, a for amplitude. And what we're going to do is go into this integral with those values now. Okay. So that's just by energy conservation. Right, so he's VA to the n because when we get to x equals a and minus a, the velocity vanishes. Those are the turning points. Okay, so we're going to go ahead and take this into this integral. So now, we'll all everything's named star. We have t is equal to, let's go ahead and just plug this in and see what we have. So we've got dx prime 2 over m. We have energy, which is b x to the n, b a to the n, sorry. B times a to the n minus b x to the n. X here. And what we're going to ask for is the period of one oscillation, period to go from A to minus A and back again. Okay. Period T of one oscillation. Okay. So X goes from A to minus A and back again. Okay, let's study this a moment. What are the boundaries if I'm going from minus a to a and back again? Well, I'm going to have to say this capital T is 2 times minus a to a, right? Because it's symmetric. If I go from a to minus a, that gets the minus sign. Go from minus a back to a, that gets the plus sign. So I have 2 of those. So let's go ahead and start. We have T equals 2 of these minus a dx. We don't have to declare a integration variable anymore, except for one. B a to the n minus x dx to the n. Okay, but we don't like that absolute value, and because we have symmetric functions here, we're going to end up with this one, 4, and then we're going to go 0 to a. Okay, see, I got that other power, I got that other factor of 2 going from 0 to a now. We can get rid of the absolute value sign, and all will be well. So we've got 2 over m, b, a to the n minus b, x to the n. This is the one we can really sink our teeth into. Now, there are only a couple values of n for which you can just do this in closed form. Otherwise, you have to start invoking special functions. And there's a way to deal with this integral where we take all of the physics out and we're just left with a number. So when you can do that, you want to do that, okay? It's not possible with all problems, but what we're going to do next is turn this into a dimensionless integral where all of these constants have been pulled out of the integral. So that's the task here. And that homework problem you guys have assigned, you're going to be able to deal with in the same way. So to make this let's just do it first, and then we'll ask commentary. Okay, we want to make this into a dimensionless integral. I'm just going to keep going this way. We've got the 4. We could pull out the root 2 over m, so we'll just do that. Root 2 over m, and what else can we pull out? We can pull out a b, so we can have root 2b over m, and 0 to a dx root a to the n minus x to the n. Well, we can do one more step here. We're going to turn this into a dimensionless integral by doing a substitution. We're going to let y equal x divided by a. Okay. So y is x divided by a, dy is equal to dx divided by a. Let's see what we have now. We have 4 divided by root 2b over m. The dx is going to be a dy, so I've got a dy. Okay. My x to the n is a to the n, y to the n. So I actually have a to the n divided by 2 dy root 1 minus y to the n. So that's the result we were after. We'll clean it up a little bit more. Okay. So yeah, when I did the x to the n, I had a to the n, y to the n. Under the square root, so I was able to pull a to the n over 2 out of the square root. And I claim, and the limits of integration are now 0 to 1. So this integral is just a number. And all of the physics is out here with these constants. So we're gonna clean them up a bit and see what we get. If I put everything under a square root, well, we can do this. So we've got an equal, we'll have 602 will have 8 m over b for whatever it's worth. But these we're going to keep outside because we have a to the 1 minus m divided by 2. And we have 0 to 1 dy root 1 minus y to the n. So this is going to cover a lot of problems. In a sense, it covers the one on the homework, but you'd have to play around with this a little. Okay. So when you do the homework, you can actually use this process, but since we have a negative power, you'll have an extra absolute value or something. We won't worry about that. I'll let you guys do that. Think of this now, just all the positive powers. The scaling law actually holds true for the negative power as well, though. So I'm going to discuss that. So when can we do this integral trivially or easily? Easily enough. And n equals 1, absolutely. No problem for n equals 1. N equals 2, that's going to be our big theme, small oscillations, harmonic oscillations. N equals minus 1, flipping the signs around, you can also do that one. The other ones you need special functions, gamma functions and stuff to express as. But on the other hand, this is simply a number. So what is this physics telling us here? So these were oscillations in, right, these were, just to make sure we had, these were the period of oscillations in a potential well. All of those functions were an oscillation of potential well. So let's see, we'll open up some space to discuss this. Okay, let's save this and open up some space over here. Here's our period of oscillations. 8m over this constant b. Amplitude to the 1 minus n divided by 2 integral 0 to 1 dy root 1 minus y over n. And the potential well was, of course, u of x equals b next to that power. Good, so let's take a look at a couple of powers of n here. If n is equal to 1, then you're basically looking at that linear potential that was more or less a free fall type of potential. Okay. So let's check these out. Check. N equals 1. T is proportional to amplitude to the 1/2 power. That's essentially the same as your law of free fall. Okay. Law of free fall, height and distance and square both sides, distance times square law, right? That's essentially like free fall. That's a 1/2. You do n equals 2, what do you get? This is the interesting one. N equals 2. What happens to the amplitude there?
0.
Yeah, amplitude to the 0. So T is proportional to amplitude to the 0th power, which is just 1. that's the harmonic oscillation. Do you guys remember in harmonic oscillations that they're amplitude independent? Period is amplitude independent. And that's what you're seeing right here. Amplitude independence of harmonic oscillation. That's where we're about to study those coming up soon. Amplitude independent. And I'm going to put the n equals minus 1 in here as well. Although for that one, you guys are going to have to do a little bit slightly different process here. Make sure you get the right sign under there. But you'll get the right scaling behavior. If you do n equals minus 1, what do you get here? Just plug it in. N equals minus 1 time proportional to, yeah, t to the amplitude to the 3/2. Where have you ever heard of such a thing? You have, you just forgot. Square both sides. What do you get if you square both sides? 4 t squared proportional to a cubed. Where have you heard of that? Kepler's third law. You guys remember Kepler's third law? Sorry?
Not ringing a bell.
It's not ringing. Oh, how about you? Kepler's third law of planetary orbits.
Yeah. I remember that.
The period squared proportional to the semi-major axis cubed.
I didn't take 4A at Fresno State. I took it at Fresno City. We did not cover
Didn't
Kepler.
go. Don't worry, we'll cover it this semester.
I think you also cover it in classical physics, P Science 131.
Yeah, we cover it. Oh, yeah. It's a great cultural moment, but nonetheless, this is something. The point here is, I'll just put here Kepler's third law for reference. We will do Kepler's laws and, gravity and everything. But the interesting point here is that you get that behavior without actually solving the differential equation. Notice we got this discussion, we got this behavior here simply by analyzing the differential equation. We didn't, the solution would have, so to speak, would have been to do this integral, but it's just a dimensional situation at this point, okay? So that's also something to keep in mind. You can get a lot of information about a system before you actually go into the nitty-gritty of a calculation. Although, this was a bit of the nitty-gritty dimensional analysis and, scaling, getting all of the constants outside of an integral. This is now just a number, so this has to be physics. Good. So on your homework, you'll essentially have this, except the B is the K, and you're going to have to see how the, you'll have to see how we deal with that, because we assumed all these B's were positive, right? You're going to have that K in that problem is negative, so you'll have to have flipped these around. The scaling behavior will still remain. Okay? The scaling behavior will remain, and I'm just going to put a note on the homework. Homework problem. What we had there was 1/2 m dx dt squared plus u of x, which was minus k over x equals minus k over L. That was that initial distance. So when you go into the integration, when you go to the separation of variables with this, it's just going to flip one of the signs around here. It's already been flipped around, okay? So you can actually follow these steps. I'm just saying don't literally use that formula, but you'll come right to that, you'll come to the same point. You probably won't have this factor here because in our problem, we only had the right side, right? The positive, we didn't have positive and negative. So that's why I say take this in step by step. You won't get that exact formula. You'll get the scaling behavior, and then that will give you the time it takes to fall into a center of attraction. T, it's not gonna be the period time to fall into the center of attraction. But this is the result we want to hold on to, because when we do study Newton gravity and Kepler's laws, this time will be related to the period of orbits of a certain case of Kepler orbits. So we're definitely going to want to hold on to this result for later on in the semester. So that was that homework problem. Attraction. Yeah. So what we're going to do next, okay, so yeah, so what we're going to do next is focus on this particular case here. And that'll take some time to go through, because that's going to be the harmonic oscillation case. Sines, cosines, the whole business here, approach from a different angle than you're used to. Good. So we kind of wrap up. Put this back up here. Just as a general topic now. So we had a very specific case here. So once again, period of oscillations. The idea is, and I'll just draw the general type of case. Suppose we have some function u of x like this. Then, for a given energy level, there are two turning points, x min and x max. And the motion is restricted to the region between these 2 points. And you can justifiably just imagine a ball rolling back and forth in a bowl of that shape. Give you roughly what's going on, right? It's oscillating back and forth. I deliberately made a non-symmetric potential well right here. Deliberately made it non-symmetric. And the period of oscillations, that is that 2 integral x min to x max. I'm just modifying the one we had with the amplitudes. X min to x max dx 2 over m e minus u of x square root, right? That's that expression that just comes from that quadrature here. So that, you could say, defines the period of oscillation in a very general sense. And some of those things we were just looking at fit right into this schema. The ones we did a minute ago, we had them symmetric about the origin. But generally speaking, you've got some, this could be a roller coaster, for instance. And you didn't get enough speed and you're down here just oscillating back and forth. Yeah, so that's the period of oscillations. And what we want to do now is get from here to the standard harmonic oscillation. So what we do for a local minimum, here I'm going to go x sub 0, so we have a minimum at x sub 0, minimum of the small oscillations. If these are just generally oscillations, you're sloshing back and forth with potential wells. So the next thing that we do, small oscillations. So what is a small oscillation? What we do is we expand this function in a Taylor series. We're going to expand u of x in a Taylor series. And we have a local minimum at x of 0. So we have the following. We have u of x, u of x of 0, u prime of x of 0, x minus x0, keep going, 1/2, u double prime of x0, x minus x0 squared. We'll add a couple, plus 1 over 3 factorial third derivative cubed. I'm going to do one more, 4 factorial fourth. This is overkill, but that's okay. Good, so we've expanded to 4th order, and this is a constant, okay? And we know we can take or leave arbitrary constants when we have potential energy. What about this next one here? What about the derivative at x of 0? X of 0 being the local minimum.
Still a constant, I would think.
What's the constant equal to?
Something to do with x naught.
Local minimum, first derivative 0. Okay. So this is 0 because we're at a local minimum. So the first non-trivial term in this is the quadratic term. And if we're at a local minimum, the cubic term will probably vanish. Okay? And the next one above that would be the Cornic term. So small oscillations are when your amplitude is so small that all of these higher orders are negligible. And that can always be done by making x minus x not sufficiently small. Okay? So that's a matter of judgment and a matter of the particular case here. So what we end up with is u of x, I'm just going to use the equal sign, it's an approximation, we end up with a half u double prime of x naught, x minus x naught squared. So that's what we call our potential energy function in the vicinity of the local minimum. And you guys remember your second derivative criterion, this second derivative is going to be positive because we're at a local minimum. Okay. Second derivative when you learn calculus. And you can say, what is small? Well, these terms have to be much, much less than this one. Okay. And again, you can always do that as long as you come close enough to x of 0. So we'll write for x minus x0 sufficiently small. Sufficiently small. Okay. We have a minute or two here. So this second derivative gets a new name. I want to leave stuff up here on the board though. Small oscillations. Yeah, what we can do here is a change of variables. I'm going go ahead and erase what's up here, okay, you guys have this, so I have the space. We're gonna do a change of variables. And that essentially means we relocate our origin. We choose the origin at x0. Or choose origin at x sub 0. Then we have now u of x, I'm keeping the same letters, 1/2 k x squared. Did you guys see that coming? K for spring constant, right? That's what the spring constant really is. It's the second derivative of your potential energy function at the equilibrium. So yeah, now we have this expression here, and if we go into that integral over there, which I'll do right underneath it, well, yeah, u of x equals 1/2 kx squared. So yeah, let me just take this piece of board here to wrap things up. So now, if u of x equals 1/2 k x squared, energy equals 1/2 k a squared, period is equal to 2, 0 to a dx 2 over m. This is nice, we get the 1/2. That's gonna cancel that. Actually, I can clean that up here. We can just operate on this thing here. So the 2 over m and the 1/2 is gonna cancel that, so it's just gonna be k over m. So we're gonna have k over m. K squared minus x squared square root. So that'll be the period of oscillations. But we can approach this in a different way as well, because we have a potential energy function. We can do Newton's law on this as well for harmonic oscillations. So we're going to pick up with this next time. This is taking us right into the study of harmonic oscillations. And we may actually do this one together on Friday. This one is a nice trig substitution that you guys may not have done for a while, so we'll try that. Good, that's all we've got for today.